Let's do a couple examples using our new result about the Laplace transform of a convolution. It's usually called the convolution theorem, but this is just the traditional name for this fact, that the Laplace transform of a convolution is the product of the individual Laplace transforms. So let's use this to find the Laplace transform of f convolve g, where f is e to the t, and g of t is sine of t. So what we're really finding here is the Laplace transform of e to the minus t convolve sine t. Now, if you needed to know this Laplace transform, imagine if you did not know the convolution theorem, imagine all the work this would be. So first you'd have to work out, right, this convolution is some big messy integral involving an integral from 0 to t of e to the minus tau times sine of t minus tau d tau. First you'd have to compute this integral, and then you'd have to compute the Laplace transform of that, which is itself another integral if you didn't have a formula for this. So this would, computing this Laplace transform without the convolution theorem would be just an awful amount of work. It seems terrible. But fortunately, we know the convolution theorem. We proved it ourselves. And we found that the Laplace transform turns a convolution into a product. So it turns Laplace transform of e to the minus t convolve sine t into the Laplace transform of e to the minus t times the Laplace transform of sine of t. And we know these individual Laplace transforms. Laplace transform of e to the minus t is 1 over s plus 1 times, and Laplace transform of sine of t is 1 over s squared plus 1. So altogether, we get 1 over s plus 1 times s squared plus 1. Okay, so, we were able to work out this Laplace transform without doing any integrals. We didn't have to use any of these awful integral definitions. We just used the convolution theorem together with a couple Laplace transforms that we already knew. So that's a pretty nice trick. Okay, well, let's do another example, but this time an example with an inverse transform. So how about the inverse Laplace transform of 1 over s squared times s squared plus 1? So again, it is possible to do this without using the convolution theorem, but we would have to do some big, awful partial fractions problem to decompose this into its partial fractions form. But now that we know the convolution theorem, we can use that to take a shortcut. So 1 over s squared times s squared plus 1, this is 1 over s squared times 1 over s squared plus 1. And so this is a product in the s world. But what the convolution theorem says is a product in the s world is convolution in the t world. So this is inverse transform of 1 over s squared convolved with the inverse transform of 1 over s squared plus 1. All right, and fortunately both of these we know. The inverse transform of 1 over s squared is t, and the inverse transform of 1 over s squared plus 1 is sine t. Okay, now depending on what you're going to do with this result, you might just leave it in this form, leave it written as a convolution. If you actually want to know what this function is, like you want a complete formula for it, then you do need to work out what this convolution is. So there's kind of a choice in what work you want to do. You either need to work out the partial fractions decomposition of this function, or work out what this convolution integral is. But it's your choice. This convolution integral is doable. It's the integral from 0 to t of tau times sine of t minus tau, which I hope looks doable. It's just a little exercise in using integration by parts, so it's not that bad. And in fact, I think that this integral would be easier to work out than the partial fractions decomposition of the thing that we started with. So in this case, the convolution theorem gives us an out. Okay, so for our final example, let's work on this. Let's find the Laplace transform of the integral, so definite integral from 0 to t, of f of tau d tau. So really what we're going to figure out here is sort of a new general Laplace transform formula for an integral, right? We have a Laplace transform formula for a derivative and for multiplication by t, but what about integral from 0 to t? Well, one thing that there's a nice way to make this very doable, which is this integral from 0 to t, that might make you think that, hey, there's something involving the convolution going on here, and you'd be right. We can write this function of t inside the Laplace transform as a convolution. It's the integral from 0 to t of f of tau times 1 d tau. So this is the stuff inside our Laplace transform. It's the convolution of f and the constant function 1. And now we can just use the Laplace transform. So before we do that, notice that what this is telling us is, right, f convolved with 1 is actually the integral of f from 0 to t. So right, this means that f convolved with 1 is not the same thing as f, right, except for special examples. This is telling us that the convolution, right, the way we write it, it kind of looks like a product, but if it is a product, 1 is not the identity of the product. So have to be a little careful with convolution. At any rate, now that we have this function of t written as a convolution, we can just use the convolution theorem. So Laplace transform of a convolution is the Laplace transform of the first function times the Laplace transform of the second function. Now the Laplace transform of f we can't know because we didn't know f to begin with, but the Laplace transform of 1 is 1 over s. So what we get here is that the Laplace transform of the integral of f from 0 to t is just 1 over s times the Laplace transform of f. This kind of makes some intuitive sense because, after all, the Laplace transform of a derivative essentially is s times the Laplace transform. There's some other terms that pop up, but a derivative is basically multiplication by s, so an integral is division by s. That kind of makes intuitive sense. But to work it out, we did use the convolution theorem. There are other ways to work out this particular derivative rule, but it's a nice example of how you can use the convolution theorem as a quick shortcut.